Please like and leave a heart. Please.
There we go. Hello, everybody, and welcome to the Vitor Luxman Show. And I totally forgot to put on my microphone. Gosh, where is that? The simple things that I forget. I haven't done the show in a minute. Wow, this is all wound up back behind here. We'll get to it. There it is. Rookie mistake. There we go. Maybe now people can hear me better. Okay, there we go. Hey, everybody, welcome to the Vitor Luxman Show, where I'm your host, David Gibson, where we're unlocking the secrets to success in the oil and gas industry. One interview, one presentation, and one technical screw-up at a time. Hopefully, that's our only technical screw-up for the day, and it's on my shoulders, which I'm more than happy to be able to put that burden on my shoulders. So happy everybody's here with us on an amazing Friday. This is the start of summer vacation, summer break. Kids are out of school. They're already sleeping in, having a fun time at the house. So today they asked if they could watch one of their favorite YouTubers today. And so hopefully they're watching right now. Hopefully I'm their favorite YouTuber. Highly doubt it, but maybe me and Mark Rover can battle it out on who's going to watch today. So, all right, guys, let me know where you're watching from. Love to be able to give you a shout out here on the show. So thankful today. Our show is brought to you by AI Driller. And here in a moment, we'll be giving away one of these bad boys. But let's say hi to a handful of people that are already watching. And of course, without, it's like clockwork at this point. Mr. John DeWart watching from Elkhart Lake, Wisconsin. That's hard to say fast. I screwed up every week. Porsche's on track today. Music to my ears. Thanks for being here, sir. Do appreciate it. Soren says, good afternoon from Copenhagen. Thank you for being here. Robert tuning in. Good morning, David and Jeff. Nice day here in Tomball, Texas. Good to hear that the weather's nice there in Tomball. Now, we've had some crazy weather in Houston here lately. All right, George tuning in from Houston, Texas. Thanks for being here. LinkedIn user, morning from Houston in the 90s. All right, a little warm. All right, and then our good friend of the show, Mr. Pete Stetson, tuning in from Dallas. Thanks for being here, sir. Do appreciate it. All right, you guys feel free to keep letting us know where you guys are watching from. Like I said, this week's episode is brought to you by AI Driller. So put in hashtag AI Driller into the comment section now for your chance to be able to win some AI Driller swag and one of these fancy 3D printed drill bits. Because if you don't have one, trust me, you want one. All right, just put in hashtag AI Driller into the comment section now. And here's a quick clip from our sponsors. Let me find it. Where is it? AI Driller intro. There we go. All right, almost clicked on the wrong thing.
Girl, I wanna hear you whisper it. Girl, I whisper it. Girl, I wanna hear you whisper it.
Wow. All right. A lot of people getting into the comment section now. I appreciate it. Here we go. So we got John, Oscar Morales, Pete, Robert, Tony Evans, Jeff. All right. John, Sandeep, Soren. All right, guys. Keep that going. Do appreciate it. Thanks for to AI Driller for sponsoring today's show. We've got LinkedIn user says, good evening, David, watching from the Middle East. I was about to say evening. That's definitely not where we're at here. So great to be able to have an international audience tuning in today. Let me get this little thing off the screen here so that we can actually see faces. There we go. Back over to the comments. Did have a couple of other people tune in. So we got Mr. Matt Isbell, one of my favorites in the industry. Every time he speaks, love to be able to hear it. I'm always listening. Like I said, Oscar tuning in. Thanks for being here. John from Texas. I don't know. I can't pronounce it. Somewhere in Florida. All right. All right, guys. Without further ado, we'd love to be able to bring on here. Let me click that twice here. somebody who I have paid attention to numerous times, been an opportunity to be in the same room as him when he was in his former capacity, Mr. or I should say Mr. Dr. Jeff Bailey. Dr. Bailey, thank you so much for being on the show today.
Thank you, David, very much for having me. It's a pleasure to be here, and I really appreciate the invitation.
Well, for those that don't know who you are, give us a quick little background.
Well, I did get a doctorate in mechanical engineering from MIT, and then I joined Exxon in 1989. And I worked in drilling initially, then I got transferred over to completions and fracturing and things like that. And then I came back into drilling in the mid-2000s by the graces of Fred Dupriest, who recognized this vibration work was important to the Fast Drill project, the limiter redesign that he's talked about.
What was it like working on that in the early days?
In the early days, it was good. We had some pull from some of the drilling organizations, but I'll get into a little bit here, but initially we were actually trying to solve bit walk, and that's how the first dynamic model was developed, to try to solve bit walk and not drilling vibrations particularly. And because we didn't reach our research objective, which was bit walk, they decided that program was no longer appropriate, and they put me on something else. You know, it's one of those things where the spin-off is much better than the original justification for a project.
Well, we can get started down one direction and find better things along the way, I guess. Well, like you spoke of there, I'll go ahead and add your presentation up here. Can you give us a little synopsis of what we'll be talking about today?
Sure. So there is an SP Distinguished Lecture video on the sp.org website. I did it actually the same year as John DeWart. It was the virtual year where we did everything remotely. And but I've taken that presentation and I've updated a little bit with, I pulled an example or two from different SP papers and dropped a few slides to sort of tune the story, you know, a little bit. So I've got this, how do we get here? So it's a little bit of the story of how this all developed over time.
Excellent. Well, I'll go ahead and let you take it away. And for anybody out there, if you guys have any questions, please put them into the comment section. I'll star them as we go through, and then after we're done, be able to bring those back up. So if there is any question that you're going to ask that might be specific to a slide or something like that, try to be able to reference it, just because we've had some trouble with that in the past couple of weeks on some of the technical presentations. But with that, nothing further. Dr. Bailey, please take it away.
Sure, and let's do questions as they come up.
Okay. Yeah, we can do that.
The slide number is in the lower right corner there.
All right.
So, well, again, thank you, David, very much for having me on the show here. So I do want to start off with acknowledgements. You know, I worked with many colleagues and managers. I saw Jeff McEachern's on the show. I worked with him some when he was at Eastern Canada, ExxonMobil. And you know, this project ended up being quite well supported by the managers. Basically, from the middle 2000s until I retired, it was strongly supported by ExxonMobil management. And there are so many people that I was involved with over the years that it's really I can't possibly name them all, but I will name three. Okay, so Fred Dupriest had a big impact on this because he recalled that I did the work in the early 90s. Which we'll talk about a little bit. And then, of course, Paul Pastusik, I worked next to him for 15 years. And, you know, we had a lot of interactions on so many projects. And the third person I'll mention is Greg Payette. You know, he's a younger person than Paul and me. And, you know, he really has a lot of energy for data and data mining. And I think he's going to have a great career. And it's really, we had many great rig trips and stuff. So I really appreciate working with Greg. But then there's like dozens of people who also were involved. And so it comes, this presentation comes from the SPDL. And I'm going to have specific references to these 6 references 5 of them are SP papers on onepetro.org. And then I do have one slide from the Kurdistan Oil and Gas Conference in London in 2014. I didn't go to that conference. The drill team sent me the slide, and I just included it because it's a good reference. So let's get started here. So yes, I hired on in '89 with Exxon, and they wanted to understand bit walk. This was before rotary steerables, and there's a lot of platform drilling where they used rotary drilling in order to gain the ROP. They did make runs with motors to make the turn, but then they went to rotary drilling. And here you see shots of it. Now we'll see a video of the movement. Okay, so the project was to take data from this apparatus and determine directional capabilities or directional tendencies of bit walk. And so we had an instrumented strain gauge at the bit that was measuring side forces and vertical forces and getting means and standard deviations and all that. But I wasn't actually able to transfer that into any knowledge about which way the bit would walk. Okay. But we did develop a dynamic model, and we used it on some wells in the early 90s off the coast of Alabama. And there was good traction with the drill team. But, again, like I said before, we didn't really solve directional walk. So they wanted to put me on a different project. But when you saw that movement, Fred always says bit is on the end of a sine wave, and I put in the cosine here, and I'll explain that in a few minutes why I put that modification in here. But certainly this apparatus inspired the dynamic modeling, and we had those early applications in the 90s. As I said here, they're promising but incomplete. But it was laid down. I worked on something else, and then Fred in middle 2000s recalled that we had this vibration effort, and we also broadened it and included torsional dynamics and involved the corporate strategic research up in New Jersey, Denise Urtas, and that became its own thing. But they were kind of coupled because they had very similar properties as two models. But so that's kind of the origin. And back in the middle 2000s, when we started to apply this, we took the C code and made a MATLAB model out of it with graphics, and we could do comparative analysis and all that. And we'd go out to drilling engineers and drill teams, and they'd be very interested. And of course, we had to work with the vendors. And so we got a lot of reactions from vendors, and there was a tremendous amount of myth busting going on. Some of the things that people said to me, which I definitely recall very strongly, are things like one person saying, you need to stabilize every connection because if it can't move, it can't vibrate. And that's a perspective that really I think is misleading. And then someone else says, we did a normal mode analysis on every BHA we ran in this field, but it didn't help, which was interesting. And then someone else said, you're telling me the exact opposite of what the vendor told me for many years. So that was also very interesting. And maybe we'll understand why in a couple minutes when I explain something. But basically, we found no comprehensive understanding of how to approach drilling vibrations and BHA design through stabilizer placement, at least that I was aware of. There was a BHA that was run in South Texas by some people, and it was, I think, developed empirically in the field as a low vibration BHA. We put it into the model and it actually looked pretty good. But I think they did not have a model that did that. It was really just empirical. So, people have figured things out empirically, but in terms of having a basic understanding through a model that could, use different parameters and come up with a prediction, I felt like the field was lacking in certain respects. And then other considerations typically govern stabilizer and contact placement. We'll get into that a little bit. But I when I had these discussions with the drill teams and the drilling engineers, it was really challenging because with all the priorities, of how to put a BHA together and what goes into, making that decision of what to run in the hole, where does this stack up in terms of priorities? And I really struggled to get the message out. So I came up with this slide, and I had 3 kids, and they all played instruments, and they were in orchestras and whatnot. And I noticed, every single time that they played, the first thing they did was they tuned their instruments, right? And so I started thinking, well, what we're doing is we're running BHAs without any tuning, right? So if you go to a concert, how would it sound if the musicians did not tune their instruments? And I think that's pretty much what we're doing in many respects in the industry is, we're running this, in some cases, multi-million-dollar hardware into the hole, turning it and putting it through huge forces and moments and whatnot, and expecting it to come out in one piece. But we're, in many cases, not even bothering to tune it, for the operating conditions we're going to put it in. So I thought maybe this was one way to sort of get to people the message that, we need to do better. We need to tune our instruments. So when I started comparing, the violin on the left with the BHA on the right, I noticed the drilling assembly is actually a lot more complicated than a violin. Okay, so a string on a violin can pretty well be represented by a second order differential equation with 2 basic fixed nodes. Down, on the bridge, there's a place where the string is, held, and then up where the musician places a finger on the fingerboard, of course, is the second node, and that length and, of course, the tension in the string determines the note that's going to be played. So you really only have 2 nodes, fixed nodes. Now, in the case of a BHA, it's a 4th order differential equation because you can't neglect bending stiffness. And then you may have possibly many nodes. In this case, and I call this a BHA with some of the worst model results we ever saw. We had 7 nodal points in the first 100 feet of the BHA. And we'll talk about this example a little bit in a minute. But the end result of this run was we sheared off part of the MWD tool, and we lost a roller reamer in the hole, and that was the only time that I recall ever losing a roller reamer in the hole. And again, this is correlated with having really bad BHA model results, and we'll talk about that more in a minute. I want to explain very graphically how this model works. And it's a force frequency response. And as you see here, the BHA, the rod there with the striped tape on it, is being pushed laterally in a up and down motion, in a reciprocating motion. And that's essentially what we're doing in this model. We're pushing on the bit with a constant force dynamically, and then we vary the RPM. And that's why I call this a cosine, because this is not a sine. We're not assuming that the bit is a node. We're actually assuming it's an antinode. We want it to be a node, but that's in the case that it's a quiet BHA. In the case of a disturbed BHA, it's actually not going to be a node. So from this excitation, we calculate states all along the BHA. We'll see that in a minute. We calculate the bending strain energy across the entire BHA, and we call that a vibration index. And then we compare that response with different BHA designs with the same amount of excitation. And we have a couple videos here just kind of showing. So in this case, we're going to move one of these blades and show a quieter response. Here we get quite a bit of displacement in the middle, but we're going to move this blade down. You'll see the response flatten out. Okay, so that's a fairly quiet response at that RPM. What we really need is a BHA that has got a quiet response across a range of RPMs. So in this, we'll show how this BHA has a smooth response across a range of rotary speeds. We're making it go faster and faster. You can see it's still pretty quiet. So that's ultimately where we'd like to go, is to get every BHA to have a flat and low response across the entire RPM range. And it's actually hard to do. There are many challenges to get there, but that's where we're trying to go. Okay, so
Dr. Bailey, before we jump into the next part, we did have a couple of questions I do want to get to. So Robert asked, how about the model that was taught by Don Daring and Bill Murr in the 1980s?
Bill Maurer.
Bill Maurer.
Right, I'm somewhat familiar with their work. I wish I had a direct answer to that question. I'm sorry, I don't. Yeah, Maurer led those DEA projects and did a bunch of stuff. I actually don't know how it compares. I'll be honest on that one.
All right. Well, now we've got a follow-up show for you, Dr. Bailey.
Yeah.
Go
okay.
ahead. Sorry.
What's the next question?
And then the next question, this is a great insightful question here. Do you feel this lack of tuning has always been a problem, or is this something newer in the industry with all of the headcount reductions and economic pressures?
No, I don't think it has anything to do with headcount reduction and economic pressures. This is fundamental physics. It's been, it's really a challenge, I would say, that gets bigger as we get more complicated tools. As we run, like in some of the deep water applications, we're running, multiple MWD tools, and then we're putting deep resistivity tools in there, and some of them are stabilized, some of them are not stabilized. And then at the top of all that, you have an underreamer, okay? So you're cutting more rock, and you're trying to manage the weight distribution between the underreamer and the bit. And I think the problem is harder when you get more complex. Now, go to the other extreme. If you just have one stabilizer on a motor, you've got only one nodal point to worry about. And I guess we talked about that a little bit at the IADD. And that becomes a simpler problem. In fact, when you don't have any stabilizers, you can't use this model because it doesn't tell you anything. This is a tool to place stabilizers. And the more complicated the BHA, the more you need to use this model.
All right. So all the questions for now. I'll turn it back over to you, sir.
Okay, thank you. Okay, so let's look back at that, what I call the worst BHA model results ever. And that's the red BHA here. We had 7 nodal points in the first 100 feet of the BHA. We busted off a piece of the tool. We lost a roller ream in the hole. And this is the only time that I had to resort to logarithms in order to display the vibration index. So here at almost 10 to the 5th, we like to have lower single digits is where our target is. And the blue is almost there. The blue gets down to 10. They were operating around 70 RPM. And so the blue BHA, one of these SPE papers analyzes this BHA comparison with like a dozen different runs. So there's more data to look at there. But the blue is pretty typical of some of the better BHAs. And we had down around 10, and this is around like 45,000. So it's a factor of 4,000 or so, thereabouts, increase in our bending strain energy in this model. Again, so, if you think about a paper clip and you're bending it back and forth without deformation, the elastic stored energy is proportional to the force or moment needed to bend the clip squared, okay? And we do this dynamically in the model. But again, this is like an enormous increase in bending strain energy for a certain given reference excitation at the bit. Okay, so that we're exciting at the bit, just like you saw in the videos, propagating the wave up the BHA, and then just summing the bending strain energy. And so every beam has 4 states. The lateral deflection, its first derivative is the angular deflection. Its derivative is a bending moment, or related to the bending moment with some constants. And that has a derivative of the shear load. And so these large discontinuities in the shear load occur where there's a huge change in the bending moment. And these are driven by the little dots here where the nodal points are. And so you can see right where there's these 2 red dots close together is where this thing starts to take off. This is why the change in that bending moment, is related to the contact force. If you think of a beam of W weight per unit length, and it's of length 2L, and you just support it in the middle, the force is going to be 2 times WL. And that force is distributed within the beam by a positive shear load to the right of the contact of plus WL, and minus WL to the left of the contact. And so the change across the contact of the shear load is 2WL, which is the contact force. So we'll go back over here, and every time that there's one of these flat sections here where the shear load is changing across the contact, that difference is the contact load. So this is a dynamic force that's required for compatibility for the BHA to stay within the borehole. Otherwise, the displacement constraint, wouldn't apply, and you wouldn't be in the borehole. So this is governed by the mechanics of the beam lying within the borehole. So yeah, when you get this huge change in the shear load, you have a large dynamic contact force. And of course, that gives you dynamic torque, which gives you difficulties in drilling. But so we take this bending moment, we sum it over the entire BHA, and we call it an index, a vibration index. So stepping up, what factors really govern stabilizer placement? And there are some common factors, which would be directional control, which certainly applies to the first 3 contacts. But a lot of the BHA really is beyond where there's the first 3 contacts in many BHAs. There's the concern to have the LWD proximity to the bit. A lot of times you're struggling to get, the tool that's most important for formation evaluation to get that close to the bit so that you don't drill much hole before you evaluate the formation. And that is legitimate concern. So you can see that there's going to be trade-offs coming here. And then there's, I've heard, we want to keep the BHA off the borehole wall. And I think what they're really getting at there is we don't want to damage the BHA. Maybe there's some unintended consequences here where we design something to keep the BHA off the borehole wall, but we end up generating more problems by doing that than if we were relaxing that constraint a little bit. And that's related to the next one, which is protect the tools. So these are some of the reasons I've heard, for stabilizer placement, and some of them are, maybe preferences, and some of them are, governed by the drilling mission of trying to get data and so forth. But not usually do people actually move stabilizers to improve the drilling dynamics. And we'll talk about this example in a minute. But so if you have a model and you're trying to tune a BHA, well, how can modeling help? The drilling client and the vendor determine the tools. I could say, well, if we don't run this under reaming tool at the top of the BHA, you can have lower vibration indices and probably have an easier time drilling as well. And it's like, well, that doesn't solve the drilling mission of under reaming the hole at the same time that we drill. So, make it work, right? Come up with the best BHA that has all these tools in it. And that goes for formation evaluation as well. We may be putting multiple formation evaluation tools in the BHA, and that's a constraint that's governed by the the drilling client and the vendor. The vendor has specific tools to do those measurements, and they're different from one vendor to the other. So we often look at rearranging tools in the string that doesn't violate any of the considerations of the proximity to the bit, or also stabilization constraints. There are magnetic effects too. Some tools have to be separated with non-mag components. And then electrical power. Some tools generate power, and that power has to be distributed up and down the BHA to provide power to other tools. You can't have all the tools above the one that generates the power, because that wouldn't work. So that's certainly a consideration. And you'd like to have a model that's simple and repeatable. You can do on almost every well, and you want to make sure you have the data available to do the kind of analysis that you want to do. I did work in fracturing for a while, and fracturing models have an unlimited number of knobs to turn to adjust the model results. And you struggle to get the data even at the borehole, and then you realize that, go out 100 feet, the formation properties start to change, and you don't have any measurement of that. So that makes fracture modeling very challenging, of course. I do want to say that in this model, there are 0 knobs to turn. The only thing you can adjust is what is or is not a nodal point. Otherwise, you're just describing the steel that's going in the hole, the OD and the ID to get the bending stiffness, and then the length and where are the contacts. You see on these diagrams a little black dot over here on the side, and that represents where the nodal point is in the model. So like I said, there's no tuning parameters in this model at all. Okay, so what is the rate BHA design question? And we came to this question, which may or may not be, depending on your perspective, but we thought it was a good one, is what is the best arrangement of components for my well in operating conditions? And so that's kind of how this tool got developed, with that sort of thought in mind.
All right, Dr. Bailey, before we jump to the next one, we did have a couple of comments and then a couple of questions. So Robert said, building a tuned BHA is easy if you only have simple drill collars and stabilizers. The plethora of new tools with differing lengths, diameters, and stiffness introduces RPM tuning problems. Just love to be able to get, if you have any comments to that to add as well.
Yeah, so one thing, if you do this a number of times, you start to realize that what you like to do is have it more constrained closer to the bit. And then as you go up away from the bit, you want to sort of relax the constraints. So if you have tools that have, very thin walls or something, or more flexible, and then you have new tools also introduce new lengths. They may not be the 30-foot lengths. You may not be able to put a pony collar in, for instance. We use pony collars quite a bit to sort of space things out. Because you have to have electrical connections, and not, pony collars typically don't have electrical connections. So, I can understand the perspective here. Yeah.
So a question from George says, what is the easiest way for me to access this model?
It is a model that is used by ExxonMobil today. I would look to take some of these lessons and apply them in a commercially available model that you have access to. Okay. There are a lot of models out there, and maybe it's phrasing the questions in a way that are instructive from these lessons.
Okay. This one says LinkedIn user, but I looked it up. I believe this is Kennedy. So Kennedy asked, David, confirm from the presenter, if this BHA presentation covers only lateral vibrations, does the presentation also cover torsional, stick slip, and vertical bit bounce vibrations?
So there isn't anything really here on bit bounce. Regarding torsional, I remember we talked about those dynamic contact forces at the going back to, let's see, here, we've got a contact here. This is a blade on a stabilizer, a nodal point here given by this red dot. And at this red dot, we have this huge dynamic contact force. So anytime you see this, you're going to have a lot of torsional, dynamics or dysfunction, really. It's going to give you a torsional dysfunction because you're obviously going to be rubbing very hard. And, we do see stabilizers come out, an inch or more under gauge sometimes. And I think it happens when we get a lot of stick slip. And stick slip is very complicated. And of course, it depends on the entire length of the string and whatnot. But I think this makes a much more torquey bottom hole assembly. And we have some data that shows that. So yes, this does indirectly affect torsional vibrations, but not as directly as you might like. So there is a specific torsional model that's a companion to this model, and that's talked about in other SV papers.
Final question for this part right here. Shane asks, what are your thoughts on incorporating a shock reduction tool into the BHA? Pros and cons.
Yeah, so there are multiple types of shock tools. Some are just axial shock tools that are typically run in a big hole, shallow. And those shock tools, I think when they have the right frequency, can do a lot of good. My understanding is that it's a challenge sometimes getting them matched properly with the other dynamics of like if you're running a roller cone bit. And then there's the torsional spring type of tool. And I think those can be very useful. But yeah, I mean, we have modeled BHAs with shock tools. The way we adopt it in the model is to reduce the effective diameter a little bit to account for a little bit. It's not as stiff as a drill collar, for instance. So we make it a little bit more flexible, but we put it into the model and can model it that way. But yes, I think shock tools can be useful.
Well, we did get one more question snuck in here real quick, Mr. Pete Stetson asks, any suggestions on commercially available vibration models?
Yeah, so I know DrillScan has some vibration models that are useful, and I have, of course, most familiarity with this one. But like I say, there may be lessons here from the way we approach the problem that could be adapted for use in some other models. Maybe think about it that way.
Excellent. All right, Dr. Bailey, I'll let you take it away.
Okay, so this is our second of 6 examples. And I think this, this question here of what is the best arrangement of components for my well and operating conditions. So I pulled this next example from an SP paper or IPTC paper. And I think it's really instructive because we had a very, an interesting opportunity here where we had used this traditional configuration in the blue and the green BHAs. There's 2 MWD tools here. One has a blade, one doesn't have a blade. And in this configuration, which is the way the tool is normally run, we drilled for a bit and then we pulled out of the hole, changed equipment, and then drilled, but then we lost the BHA here. I can't remember the exact reason why, but we had to sidetrack, and so we started shallower and came down with a different assembly, and we were allowed to make some changes here to the assembly. We were able to swap those 2 tools, and we also insert another drill collar to space out to this next stabilizer. And so we ran the red and the pink BHAs in basically the same rock parallel to the original borehole. So we're drilling the same rock. All we did was swap the tools. And then it made for a very interesting data set. Okay, so here are the model results. Again, we have the vibration index on this vertical axis and RPM is on this horizontal axis. You can see that the pink and the red BHA has a much lower and wider, we call sweet spot, starting at 100 RPM and going up to 200 RPM. And, when we do have stick slip, we understand that, the BHA is going to be going through a range of rotary speeds. So we typically like to see something like this, where we have a low and flat and wide RPM range that's we call a sweet spot. Now, the blue and the green BHA isn't really bad. I mean, it comes below a value of 5 at 160, and we are going to be drilling typically about 160. So, I mean, this isn't a bad response here on the primary response. This is a second mode where we excited at like 2 times the excitation frequency. So it does have a bit of a resonance showing up here, which isn't great. Of course, this one has, the pink and the red have resonances there, but down here, you're off the peak at 160 to 170. So we would say that the red and pink have better response than the blue and the green in the model, and we would naturally select it based on just the dynamic model results. So we did get the data from these 4 runs, and the sidetrack results demonstrated vibration reduction. We had 21% higher ROP on average and we were able to run 25% higher weight on bit operating at the similar rotary speed range. And even though we had more weight on bit and higher ROP, we had similar stick slip and torsional vibes, but we had a 50% reduction in MWD lateral vibrations and a 69% reduction in shock peaks. I should have had torque in here, but I didn't. Sorry for that, but you can see that on average, we're drilling faster, we're pushing harder on the bit. We must have had more torque. But the lateral vibrations and the shock peaks all were reduced. And so we were, very enthusiastic about those results. So here's some population distributions. On this axis, there's the RPM, and the shock peak is coming down here towards you. For the blue and the green, you can see that there's really pretty substantial shock peaks of 20 Gs or more, really across the RPM range. There's no real sweet spot. Maybe it's a little bit better in this one at 160 than at 180 or at 140. But if you look over here at the red and the pink, we've got much lower shock peaks, and it's like very significant improvement in our shock peak results. So we're drilling faster, we're able to carry more weight on bit, and getting about the same stick slip, and much lower lateral vibrations and shock peaks. So this well gets finished, and they're drilling the next well. Which BHA do you think they would use on the next well? Well, of course, they went back to the blue and the green configuration because that's their standard configuration. And this is an opportunity where the proximity of the LWD tool to the bit is a more dominant design choice for the drill team and the vendor in this particular situation. Even though we demonstrated lower vibrations, faster drilling, and higher ROP, with the alternate configuration. So kind of instructive, what are the priorities? And of course, what I would like to see would be going back to the drawing board and saying, well, where could we position the blade on this tool, still get about the same proximity to the bit, but maybe not have this drilling dysfunction? But that would require a redesign of the tool, and of course, there's nothing you can do in the field at that level. So let's look at the third example here, which is high angle reaming while drilling in pretty much a softer formation. There was a big amount of discussion between the vendor and the drilling engineer who really supported our redesign effort. And this BHA was a compromise in the first place because the vendor did not want to put the pony in between the underreamer and the stabilizer. But you can see that the red characteristic at the the operating RPM of 140 is about 40 times greater than the predicted, calculated model results at that rotary speed. And we have actually in this BHA 11 meters between the under-reaming tool and the next stabilizer. And that was something that at the time was very unconventional and something they really didn't want to do. That was considered too much spacing. And I think part of it had to do with just sort of general practice, but also thinking, hey, this is basically a horizontal well. What's going to happen, with the under-reamer not being centralized in the hole, right where it's operating. So that was a big concern. But the results are pretty good. They were able to drill with 24,000 pounds average, 88-degree hole angle, 130 RPM, which is pretty close to the sweet spot. They made 41 average meters per hour and up to 69 meters per hour. Lateral vibrations were typically less than 2 Gs. Low stick slip, sticking ratio less than 0.4. And they actually said in the report, 0 axial vibrations. This was actually on a platform where ExxonMobil had just taken over operatorship, and there had been 21 other wells that had already been drilled with the same vendor, and their average ROP was 13.5 meters per hour. And on this first well, we obtained 41 meters per hour. So it was about a 3 times ROP improvement with this particular BHA. And again, the main difference here is putting 11 meters between the under-reaming tool and the stabilizer, removing one of these nodal points, and it's pretty much stabilized the same on top as the original BHA. And I guess we took off a couple of drill collars. But they were pleased with this BHA and used it on many of the successive wells in this field. So this fourth case study, this is a slide that I actually did not write. It came directly from the drill team, and they presented it in a poster session at this Kurdistan Oil and Gas Conference in 2014 in London. And they cited 2 hole enlargement while drilling BHA designs, the 14¾ by 17 inch and the 8.5 by 9.5, 726 meters here, 790 meters here. They did these in one run, each of them. They're citing 6.5 meters per hour and 4.5 meters per hour. And they wrote this longest and fastest hole enlargement while drilling ever recorded in Iraq. And they saved 12 days of rig time by avoiding separate hole enlargement run. And the reason they got into this situation is because of H2S concerns. They had very thick wall casing, and they actually tried to run alternative designs, but they couldn't get the BHA to bottom actually because of the constraints on the well. So they ended up wanting to place these stabilizers spaced apart from the under-reaming tools, and they basically sent me a design and said, "How does this look in the model?" And I wrote back, with the results, "Hey, it looks great. Go ahead and run it." And they did, and this was the result. So sometimes, we try to push from the model side, and sometimes the field pushes back and says, "This is what we have to do. How's it look?" Same thing happened with some of the deep directional resistivity tools. One of the vendor doesn't really stabilize them, and when they started running those BHA designs initially, it was like, "Hey, this looks really great," and they had good results. So spacing out is kind of one of the things that comes out of this this model. So number 5 here, our second to last example, turbine BHA in a deep well. This is unusual in that it is the first time that this model was actually operated and run by a drilling engineer working within a drill team. And this person actually was an unusual drilling engineer. He had a PhD and started the research company, but he had some very interesting results here. So he inserted this pony here in this red BHA initially because that had lower vibration indices than before he had the pony in there. So he thought he was working towards optimization. He ran this 3 times, and they really didn't drill very far on each of the run, and they pulled out several times. And he decided that there was a case to really look at an alternative BHA because they weren't getting very far fast. So took out the pony collar and took out the stabilizer and came up with this green design. And there's a factor of 8 reduction in the vibration index at the surface rotary speed of like 30 to 40 RPM. And the ROP improved. They had 5 runs to TD, as shown in this chart. The ROP increased 60%. The run hours are up 68%. The interval length increased an average of 150%, and the MSSE declined. What I found was really interesting was what happened with the bits. In the red BHA, they were coming out whole with 1-1 and a 2-4 and another 1-1. So they weren't really getting weight to bit. And unfortunately, we don't have pictures of the stabilizers to show what they looked like. But, why was it that they weren't actually getting any weight to bit and they were coming out of the hole with very low ROP? But the green BHA, the first one, they got a 7-8 on their bit. So these were diamond impreg bits. So they're obviously now they're getting weight to bit. The bit is wearing as they're cutting the rock, and they're making more hole and faster ROP and whatnot. So, you can see that we're getting more weight to bit in the green BHA and the red BHA. And the only thing that changed was the change in the spacing of the stabilizers and the decrease in the vibration index accordingly. So our last example, this is a large hole size rotary steerable BHA design. And before we got to these 2 runs, they'd actually tried probably 6 different BHA designs until we got here with various amounts of stabilizers. Not really happy with the results. So the red BHA, they had this flex sub in here between the LWD and the rotary steerable. And they thought it was needed for a directional performance in order to make the turn. They really were only getting, 3 degrees curvature, but it was still recommended, I guess, at the time. But it does 2 things. It increases the length between these 2 nodes, but it also reduces the effective OD because it's a thinner, wall, narrower diameter than the tools around it. So here's the vibration index results, and they were operating around 160 RPM. And the vibration index is actually less than a half for the green BHA, less than a 0.4. So that's really an extremely good result in the model. And the red BHA is about 3 times greater at this RPM range. Okay, so they drilled, and these are the population distributions of the lateral vibrations. We've got RPM on this axis and viblat on this axis. The average for the red BHA was 1.8, and the average for the green BHA was 0.6, which is a factor of 3, which is exactly what was calculated here, which I'll tell you, this is a miracle, actually, because we don't typically give this kind of correspondence between the vibration index and the vibration measurements, but it's pretty astounding that, there's this factor of 3 difference right here. To me, it says, we're barking up the right tree. So this is a very interesting, I don't know if any of you know Lei Wang, he's now at Parker, but he came up with these charts, which are very interesting. We've got rotary speed on the x-axis and surface weight on bit on the y-axis. And then the dots are the vibration levels. We actually see for the red BHA, there's a bit of a sweet spot down here at the calculated sweet spot rotary speed range that we had. There's red dots to the left and there's red dots and yellow dots to the right, but we do have a bit of a sweet spot in here. What's interesting, though, is across the top, it's red all the way. So above 30,000 pounds weight on bit, we've got high levels of vibrations in this red BHA. If we look at the green BHA, we've got a sweet spot at about 160 RPM, and we see, red and yellow dots to the left and red and yellow dots to the right. And at our preferred rotary speed of 160, we've got mostly green and blue dots all the way up to 50,000 pounds weight on bit. So, here we're able to actually carry much more weight on bit with the green BHA than the red BHA, because the flex sub introduces this, flexibility in the BHA, and we want to have stiffness, and because we're operating, at a non-preferred rotary speed as well for that BHA. So this is a very insightful example of what we're achieving when we, are able to get a good low sweet spot and maintain stiffness along the BHA. Getting back to the question about, well, we introduce new tools with, various configurations. Well, here we had a smaller diameter tool, and it introduced something that gave us a dysfunction at high weight on bit. So takeaways, and we can open this up for discussion, but I just want to make a few points here. I think this work basically proves that drilling performance does vary with stabilizer position. And it's important to remember that the natural frequency of a span varies as 1 over the length squared. So, if you just think about that when you move contact positions, it's got 1 over length squared sort of dynamics going on. Harmonic analysis can lead to insights on effective BHA redesign, and we target sweet spot rotary speed ranges by adjusting contact locations. This is done, routinely using this model. And kind of stepping back a little bit, what are some of my observations? Well, operators rely on the service vendors to show up on location with optimized equipment. So this model helps us get to that location or to that position with the vendor, but it's a really hard problem to solve when there are limited design variables only weeks before drilling. And in some cases, like, we swapped those 2 MWD tools, really we're talking about a year or more if we go back to the drawing board and say, let's generate a new tool that has a different contact location, because we believe that we'll have, based on some results, some modeling results, better dynamics. So, you start to think of, going back into the design cycle with some of these concepts. And we realize there may be design trade-offs that are there. Proximity of the LWT tool to the bit is obviously very critical. In some cases, we prefer to choose that over knowing that we have lower vibrations with a certain configuration. But if the service industry really embraces BHA vibration design mitigation and kind of takes that to heart, then I think there could be more concepts to accomplish this. And then I would add that we do prefer first field tests in wells of lower financial risk exposure, and this of course depends on the risk of the mitigation concept. In many of these cases, we were just tweaking BHAs, and that's how we kind of sold it to the vendor and the drilling engineers. Hey, all we're doing is sticking a pony collar in here, or we're moving this, contact up 1 collar. It's not that different from what you're going to run anyways, but it looks better in the model. And they go, okay. So, in this case, we were able to address many low risk mitigation concepts and get it accepted by the combined drill team and the vendor. And in some other cases, I'll frankly tell you that we weren't able to achieve what I believe was a good resolution because there were too many constraints. So just some observations on what needs to happen next, I believe, to sort of push this further within the industry. So any further questions or open up for discussion?
Yeah, we've definitely got some questions here. We'll go back and we'll kind of try to go in order here. So Duncan Blue asks, after the model tweaking, do you suggest monitoring with MSE or just looking at torque and shock?
Yeah, so The basic concept is to do the best job you can optimizing your BHA design and turn it over to the drill team, and they use their best practices for operating with the best results. That includes MSSE monitoring, looking at shocks and torque and whatnot. But this is really the upfront design. We do suggest hey, this might be a good rotary speed to look at, but there are many cases where you go from the design, and when they actually screw the tools together and give you a BHA from the strap dimensions at the rig, there can be some subtle changes because they picked up, tool A instead of tool B, and they give us the dimensions for A, but B is a little bit different. So there's always a little bit of, I guess, wiggle room around some of these numbers based on variations in field components.
Okay. George asks, do you have experience using soft torque systems, software tool added to top drive? If so, do you find them to be effective / helpful?
Yes, soft torque and soft speed are good systems, and yes, they are helpful.
All right.
I kind of think that every rig should have it. That's an interesting question. If you think about places where you don't normally think you need soft boundary conditions of the surface, like say West Coast of Africa, we don't have stick slip there. The rock's pretty soft. Well, think about it. If you're going in with 5 7/8 drill pipe, what if you're able to go to 5 1/2 inch drill pipe, and then you'd have less ECD, and you would be able to, solve that problem with the smaller drill string. Then you still want to mitigate your torsional vibrations. So I think there's a role for these systems in almost any application because it gives you the freedom to adjust other design parameters. And that's a whole nother technology branch that we looked at with the torsional model.
The interesting way to look at, reduction of vibrations helps ECD.
Yeah.
It's probably the first time I've ever heard those two correlated. Shane asks, what relationship does the growing utilization of bigger, better agitators in the BHA have on catastrophic levels of shock and vibration and the new need to fine-tune BHA components to optimize drilling? Are these self-inflicted problems?
I've seen some data from these agitator tools. We didn't actually look at it in terms of how it affects the BHA. So I did analysis of some rotary steerable BHAs where agitators were used, but they're typically 5,000 feet or so away from the BHA. So I thought that it didn't really have that much of a direct impact. And we did run and have run under-reaming tools or reaming tools. Fixed blade reaming tools, and we typically would run that several joints of pipe above the top of the BHA, and at some point it becomes if it's within 100 feet or so, it can interact with the model, and we typically would model it. But if it's several hundred feet away, we believe that it's far enough that it's not going to interact with the BHA dynamics so much.
Next question, is there any tool available or recommended so we can evaluate BHA?
Again, there are a number of commercial models out there. This model is not available commercially, but some of these ideas, like some of the vendors themselves have their own dynamic models. Both Halliburton and SLB have models. And you can pose a question to them, what are some of the alternative design configurations and what do they look like in the model that you use? There's some benefit to that because the vendor typically has a fair amount of confidence in their own model and have experience using it and calibrating it. And so if you ask the question for them to employ it with their model, then they're on firm ground for their technology basis, and then pose the questions of, well, if we made this adjustment to the BHA, what would that look like in your model? And then start going down that road may be productive. And again, the dual scan model, I believe, can do similar things to what we're talking about here.
Excellent. So I want to say a quick comment. Is this vibration data a composite from recorded mode and real time, or just real time? I'm assuming since some of these are RSS, it's SLB tools. Depending upon programming, MWD and RSS data points sent up hole typically are the max value over an interval of time. There may be more insights to yield. However, this is pretty interesting that they are paying attention to this specific drilling mechanic for decision making.
Yeah, so most of this is MWD data that's sent to the surface, recorded by the surface equipment. I don't think I have any examples here. I mean, we have looked at recorded mode data, and it typically will say similar things. But this is data recorded by the WIT system at the surface, is what I've showed today.
That's available there for everybody. Just a quick compliment for us from Marlon says, "What a great presentation! Thank you, Jeff/David. You're welcome. That's what we do the show for. Thank the sponsor, AI Drillers. Speaking of which, hashtag AI Driller. Put that in the comment section now for your chance to win here in a minute." One last comment or question here. In many cases, agitators are run alongside BHA assembly. Please confirm if this practice is effective to minimize vibrations.
I don't have experience with running an agitator right next to the BHA. I did have an experience where someone thought that it was a good idea to put a stabilizer above and below a motor, and it had a very interesting effect. They're drilling at 100 RPM, and it had a nice sweet spot at that rotary speed, but at zero weight on bit, actually at 100 RPM, it generated a huge resonance. And so in this case, this is before the effects of tool joints going through rotating heads was known. Every time the tool joint would go through the rotating head, they lost weight on bit, and this tool started to vibrate. And a directional driller said, the BHA goes crazy, every 30 feet, and he couldn't understand it. And I happened to be doing the modeling at the same time that they were observing this at the surface and talking with the remote operating center in Houston. And so I said, hey, take that stabilizer off the top of the motor. It's not helping you.
All right, we've got a great question here from Robert. If you could do only one, Jeff, would you opt to tune the BHA or tune the drilling process?
Oh, that's a tough question. I think going in the hole with the best BHA possible is going to give you, on average, the best results, because it's you can go with a very dysfunctional BHA like that one that had 7 nodal points in the first 100 feet, and there's something I want to talk about in that regard. I didn't really mention it in the presentation, but if you go back to, can I share my screen a minute?
Yeah, I got it back up
Okay.
there.
So if you said, oh, I don't believe this, BS about exciting at the bit and watching what happens going up hole, what if the drill string is shaking like this, and I want to get the BHA that has the least amount of motion at the bit when I do this at the top of the BHA? What would happen is you would come up with exactly the opposite results of what we have, because if you go like this with a red BHA, you're going to have very little motion down at the bit, much less than the blue BHA. So you'd say, well, that's the better BHA. But every single case that I saw said that would be, the reverse result of what we have. Okay, so you take all the results that we proved in the field, give us better data, and you'd say all that is wrong, and flip it around. So I think when people have problem with this model, what they're thinking about is they're shaking the BHA at the top by the drill string with some kind of reference excitation, and seeing what happens as you go down the BHA, and you want to quiet down at the bottom of the where the bit is, and that would lead to exactly the opposite results of what we have here.
Very insightful. So, another quick comment. Jeff, really enjoyed your presentation and your candidness on application results. Thanks, David, for another great speaker on your Vidor Locksmith show. Well, John, you're more than welcome. Once again, thanks to our sponsor. A couple of people put in a little hashtag AI driller. Thanks for doing that, guys. Another question here from Kennedy. Kennedy's figuring out that he comes up as LinkedIn user, so he's putting this in. Please, what is the best position for agitator and drill string assembly in order to minimize vibrations?
Okay, so kind of getting back to what I was saying, if you go this 1 over L squared, right? The influence of an excitation, at least in the lateral sense, goes as 1 over L squared. So if you go several hundred feet away from the BHA, to me, it's almost like going to infinity. It shouldn't have effect on lateral vibrations. With regards to axial vibrations, I think you could get some influence, but I think if you don't have it really close to the BHA, several hundred feet away, you're giving yourself a little bit of latitude that you're not actually just pounding on the BHA.
All righty. Well, Dr. Bailey, thank you so much for being here with us today. A couple of people saying, great show today, David. Thanks so much for your insights, Jeff. Thank you, David, for the efforts. Also, special thanks to Jeff. This is a wonderful presentation. So lots of people out there enjoying your work.
Thank you very much, David. I really appreciate you inviting me to the show.
Well, it's definitely one of these things we're probably going to have you come back again and do even more. I know that this isn't the only topic that you can talk on. So let me do this real quick. So guys, if you haven't, please be sure to put in, I'll do the little thing where it goes across the screen. AI driller, right? This is what makes the show possible. There are our sponsors and you out there liking, sharing, commenting. So if you guys enjoy the show, please share this. This is what helps be able to keep this thing going, so that when I call people up and say, hey, do you want to come be on the Vidor Locksmith show, they've actually heard of it before. Because we're still trying to get the word out there. And I completely forgot about this before I do this. This is the 5-year anniversary of the show. So Dr. Bailey, thank you for being the 5-year anniversary guest. I don't know, we've done over 150 something episodes. So thank you so much for that. And thank you for everybody out there if you've commented on today's show, on a previous show, if you've liked it, if you've shared it, if you talked about it with somebody, even if you watched only 3 seconds before in the past, I truly do appreciate it. So with that said, there we go. Let's see, share screen. Let's do a giveaway real quick. Let's put this up there, share. All right, come back over here to the studio, add to stage. There we go. Go back over here, and 3, 2, 1. Yep, 26 entries. All right, guys. Thank you guys all so much for watching. Do appreciate it. Like I said, it's the 5-year anniversary of the Vidor Locksmith show. Had no idea we would be getting to this point with it. And our winner of this week is Junichi, a former guest on the show and a friend. So, Junichi, you are the winner of a 3D printed drill bit, sir. I'll reach out to you, get in touch with you. We'll get this sent over to you, sir. Thanks for participating and being here. Once again, Dr. Bailey, thank you so much for being on the show. Any last words, anything you'd like to be able to share with the audience out there?
So we could do a show on torsional dynamics, maybe have some other people involved as well.
Oh, all right. All right. If you would like to see a episode on torsional dynamics with Dr. Bailey and friends, leave us a comment, leave me a comment, shoot me a DM, something like that. And we'll be sure to do it. So, there we go. And Judici says, great show. Glad he was watching. He's one of the few that's probably watching on Facebook. That's great. All right, guys. that's it for me. Have a wonderful, wonderful start to your summer holiday season. Keep the kids outside and playing. Keep them also hydrated. Wow. 5-year anniversary. Thank you guys all so much for taking part in this and making the show what it is. And as always, know your industry.